This week we meet the unsung hero of the science world, mathematics. It's the drive behind the engineering that makes the world tick. From construction sites to traffic lights to air traffic control. But this week we're looking at how maths governs how nature works as well, and can even be used to predict how we as human beings behave. First, I'm off to Victoria University to meet mathematician Dylan Mayhew. He's going to try to convince this chemist that maths is the most special of sciences. Dylan, what's the difference between mathematics and other sciences?
Mathematics doesn't rely upon experimentation. So we don't get our knowledge from running experiments and making observations. We get our knowledge from making logical deductions. So I can illustrate the difference between experimentation and deduction with an example.
Okay.
Let's do some sums. What's 1 plus 2?
3.
Yes, that's very good. And what's 1 plus 2 plus 3?
6.
Excellent. And 1 plus 2 plus 3 plus 4?
That's 10.
You're really very good at this.
Yes, I am.
But what if I asked you to add up 1 plus 2 plus 3 all the way to 100? What would you do then?
I'd look to you.
Yeah, and you would hope that there's a formula.
Yeah.
And there is. Let's see if we can figure out what it is. So 3 is equal to 2 times 3 divided by 2.
Right.
6 is equal to 3 times 4 divided by 2. And 10 is equal to 4 times 5 divided by 2.
Right.
And notice that the first number here is always the last number in the sum. So that lets us predict that the general formula, if I take the numbers 1 plus 2 plus 3 all the way up to some unspecified number, which I'll just call n, the answer is going to be that last number, n, times the next number, n plus 1, divided by 2. Do you want to try it out?
All right, let's do it. So what should we go to?
Let's say n is equal to 7.
So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 7 is equal to 28. So using that, 7 times 8 divided by 2 is equal to 56 divided by 2, which is equal to 28. It's equal to 28.
It's like magic, isn't it?
Ah, voila. So how do you know that this is always going to work?
If mathematics were an experimental science, all we could do is test the first 100 cases, or maybe test the first 1 billion cases. But would that be enough?
Well, it tells you that it's always true for those numbers.
Right, but how would we know that it works for 1 billion and 1?
Well, I'd look to you.
Yeah, exactly. Experimentation cannot tell us that this always works. Instead, we have to use deductive logic. So here's how we can show that it always works. I'm going to take these numbers, 1 plus 2 plus 3, all the way up to n, and I'm going to write the same series of numbers underneath, but in reverse order. So I'll write n plus n minus 1 plus n minus 2, all the way down to 1.
Okay.
Now notice that this top row adds to exactly the same quantity as the bottom row.
Yeah.
They're the same numbers, just in a different order. So now I'm going to add the top and the bottom row together, and I'm going to do it column by column. What's the sum of these two numbers?
N plus 1.
N plus 1.
In fact, every single column adds to n plus 1. 2 plus n.
Okay, so what's this total? I've got how many collections of n plus 1?
Well, the amount of numbers, so whatever n is.
Exactly, whatever n is. So I've got n lots of n plus 1, so that's n times n plus 1. But the sum of the top row is equal to half the sum of the bottom row, so I take that quantity and divide by 2.
Which is that one?
It's exactly the formula we predicted. So now we know that it's always going to work.
Dylan, this is great for a bunch of numbers, but what does this tell me about the real world?
A mathematician can do mathematics for exactly the same reasons that an artist can do art, to make something beautiful, to add to our heritage. So if you think this is beautiful, well, that's enough. But of course, mathematics is also useful, and it's useful because we can use it to model the natural world. For reasons that I don't really understand, it seems as though the natural world runs on mathematics. So if we want to model a process in the natural world, then mathematics is the best language to do it.
So what kind of examples can you give me?
Well, suppose that I want to drop an object from a height, and I want to figure out how long it's going to take to hit the ground. How can I do that?
Oh, you'd have to know a few things first.
You need to know the formula. And it's a mathematical formula because the natural world seems to run on mathematics.
Right.
So here's the formula. So the time it takes for the object to fall is equal to the square root of 2 times the height you drop it from, divided by 9.81.
Looks nice and simple. Should we test it?
I don't see why not.
All right.
Let's go.
Oh, looks cold.
Well, it's cold and windy.
But in the name of science, I guess, eh?
In the name of science. So what we're going to do, in honour of Isaac Newton, is drop this apple from this balcony, and I'm going to use that formula to predict how long it takes to hit the ground.
Right, and what do we need to know?
We need to know a couple of things. We need to know how high the drop is.
Okay.
To figure that out, I need you down there with a tape measure.
Right, done. The mathematical truths that Newton discovered in the 17th century are just as true today and will remain true forever. A certainty that is seldom achieved in any other field.
Right. 9.6 metres.
Now we have the height of the drop, Dylan can solve his equation.
Take the square root. 1.4 seconds. So you ready?
Yeah, go for it.
This is the moment of truth.
Okay.
On 3.
Okay.
1, 2, 3.
I got 1.36 seconds.
Well, I predicted 1.4.
So that's close as.
That's pretty good.
That was a little bit of physics to get us started. But up next, we meet a brave mathematician taking on the terrifyingly complex world of biology in an attempt to answer some of evolution's biggest questions. When we think of maths being used in science, we immediately think of physics. But Mike Steele is one mathematician who is using his skills to advance the massively complex field of biology. So we've come to Auckland Zoo to talk about how maths and evolution have become entwined.
Today, I think there's a growing recognition that mathematics is really essential in biology. I've heard it said that biology is the new physics. I mean, it's an area that is ripe for applying mathematics.
Is this exciting for you as a mathematician to tackle something as huge as biology?
Yeah, it is. It's a very exciting field. I've particularly concentrated on evolutionary biology and genetics.
The advances in the field of genetics in the last 10 years have been utterly enormous. The sequencing of the human genome 10 or so years ago cost hundreds of millions of dollars. Now there is talk of a $1,000 genome. What this means for science is that there is now an incomprehensible amount of information that can no longer be processed by traditional means.
The progress in DNA sequencing technology is absolutely fantastic. We've had to, I guess, develop whole new techniques to deal with problems that hadn't been seen before. Today, there is so much genetic data being produced by modern sequencing techniques that you really need mathematics, computer science, statistics to make sense of it. Otherwise, it's just a big jumble of nonsense. So mathematics is seen as absolutely essential in modern biology.
Sequencing basically determines the order of the 4 nucleotide bases in DNA. These are represented by the letters A, C, G, and T. However, modern techniques produce billions of these bases. Mike is finding ways to use his maths to interpret all this data. But before he tells me about his research, I need a quick tutorial on how scientists figure out how related 2 organisms are. The traditional method is to simply compare the sequence of the bases.
I'll give you a simple example here with a pack of cards. So, as you know, DNA has, and RNA has 4 bases, and so we have 4 suits of cards in a pack. Let's suppose we're 2 totally different species. Maybe I'm a bacteria and you're a monkey, okay? So our DNA shouldn't have a huge amount in common if we look at a particular gene, and we're going to lay them down as though we were laying out our DNA, and we're going to say, how often do we find a match? How often is your suit or DNA base the same as mine? Okay. So I'll put my first base down.
Yep. So nothing.
Next one.
Match. No match.
Maybe one more just for good measure. Okay, actually that time we didn't even get a single match.
Right.
Okay, so that's what we expect to see. We're not going to see much similarity. On average, 1 in 4 times we'll get a match.
So the rule of thumb would be that the more matches, the more closely related the organisms are. But sometimes, this simplistic view can throw up some baffling results. This is where Mike and his maths comes in. He has created an ingenious mathematical system that has solved one of nature's most confusing problems.
Well, our main interest is in situations where the process of evolution has changed in very strange ways. A good example of that is what happens with birds and mammals.
The fossil record had led to the belief that birds had evolved from the reptile family. However, new genetic data was throwing up a lot of DNA matches between birds and mammals, suggesting that the evolutionary tree had grown in a very different way. However, Mike and his maths discovered that nature was actually playing with a loaded deck.
What happened with the bird and mammal data was that independently the concentration of two of the letters, C and G, increased. And so it's a little bit like having a loaded pack of cards. So here we've got cards where I've taken most of the black cards. I've got a few reds in as well, but they're mostly clubs and spades. And so now if I do the same thing and we divide them in half, we might start to see some matches.
There's one, another, two, nothing.
Two. Okay, so we get more similarity, even though there's no relationship between these two patterns. Just by chance alone, because we've changed the frequencies of these suits in the pack, we will get matches. This might mislead us into thinking somehow that we were more closely related than we are otherwise.
So the random processes of evolution had shortened the odds of DNA matches between birds and mammals, falsely suggesting that they were closely related. There was no method that biologists had to account for this, so they came to Mike for a solution.
Well, the maths comes in two ways. First of all, it helps us understand what's going on, but more importantly, it helps us come up with new methods that biologists can apply to data. And when we did this to this bird mammal data, what we found was that it put the mammals back where they belong, in the right part of the tree.
Mike's mathematics has changed the face of genetic matching and has been used all over the world to correct for any misleading DNA signals.
I'm, if you like, an old-fashioned mathematician. I work with a blackboard and a piece of paper because a lot of the stuff we do is trying to come up with the ideas that others then later program into algorithms or whatever. So it's a great reward when you do some work and it makes total sense of their data, which before didn't make any sense at all.
Every day we try to find the best way to do things, from the quickest route to work to the most efficient way to run our errands. In mathematics, this is called optimization, and it lies behind everything, from the sequence of traffic lights to the price of rugby tickets. Andy Philpott at the University of Auckland is investigating how optimization can be used in the New Zealand electricity market.
Many businesses use optimization tools to try and come up with optimum production plans, sales plans, marketing plans, and trying to integrate the whole of that into a strategy that maximizes profit.
But the big problem is that in business you have competitors, and if they change their actions, this can mean that your optimal strategy for maximizing profit is suddenly no longer optimal.
So you can imagine an electricity company tries to decide what to charge for its electricity. They may do an optimization that says, you should charge $5 a megawatt hour, puts that into the market, and suddenly someone else says, well, I'm going to charge $4.50, and they can't sell any because everyone's going to buy it from the cheapest supplier.
How do you account for competition in your model?
We use a different concept from optimization. We use something called game theory.
Here's a simple example of how game theory works: noughts and crosses. There are two competitors and a couple of rules. My opponent and I play for a while, and I win a few, and he wins a few. But pretty soon, we start to get good at this game, and every single game ends in a draw. This is called an equilibrium. Because of the rules of the game, the same result is unavoidable if we both optimize our performances. It's not to my advantage to change my tactics unless my opponent changes his, and vice versa. Mathematicians use game theory to model and predict these equilibria, the predicted outcomes for a certain set of rules.
Game theory can be applied in many different economic contexts, and it has been. But it's particularly useful in electricity markets because these are designed markets, and there are mechanisms and rules that are designed that allow you to very precisely define the game that people play.
Because the New Zealand electricity market only has 5 major companies or players, the actions of one company can have a huge effect. As a result, it is heavily regulated in an attempt to ensure that these players play fair.
The purpose of the market design is several-fold. The design is really intended to try and maximise ultimately the welfare of consumers of electricity. So it's supposed to deliver electricity to everyone in the most efficient way in the short term, but also to try and produce prices that stimulate investment over the long term. Both of these things are important in ensuring you get a long-run, secure and inexpensive supply of electricity.
So optimising the market design is utterly crucial to ensure that we get cheap electricity and the industry continues to progress. However, it's no easy task because the electricity market is extremely complicated.
If you get the design wrong, then you might have unforeseen consequences of this, where people exploit deficiencies in the market and don't give you the results that you hope for.
This is why Andy founded the Electric Power Optimisation Centre at the University of Auckland. What better way to explore game theory in the electricity market than to create a game? I have the feeling I'm going to get owned. This game is a very simple representation of the New Zealand electricity market. Each player takes on the role of an electricity company and tries to make some money. Yes. So in the first round I've made $23,000. Now I need to go and see where that electricity went, where demand is, where the supply is going, what the prices of all the other electricity is in the country, and adjust my prices accordingly and see if I can make a bit more money.
The simulator is a very coarse approximation to what really happens in reality, but it does illuminate some of the effects that you might see.
Well, I just made a mil, that was pretty good. I think I could have made more. I've got a good feeling about this round. Oh no! Nobody wanted that. Priced myself out of the market, but now I've got cocky.
You shouldn't announce your feelings to the world.
A bit of advice from the game's co-creator there. Probably best to learn to walk before I run. This might be good fun, but it has a serious application for the mathematicians using it.
You know, we played it like a game of Monopoly, right? Yeah. But actually it's more than that. It's a simulation that says, what would happen if these players did this and this player did that?
The other player here is Golbon Zachary. She's been investigating whether changes to the rules of the market might have undesirable results.
Well, when I found out about game theory, I honestly felt this is what I want to do with my life. You know, it's kind of like a calling.
Golbon has been applying this passion to a recent change in the electricity industry when the government forced the sale of 2 hydroelectric power stations from Meridian Energy to Genesis Energy.
I felt there are a number of questions here in the asset swap suggestion that needed answers. We had precisely the right tools to help examine the ideas that I had with respect to the asset swaps.
The intention of this asset swap was to increase competition and bring down prices for customers. So Golbon investigated whether this would always be the case.
The suggestion of asset swaps had been arrived at through a specific study that highlighted situations of dry winter. So a natural question that came out of this was, would this asset swap also be a good idea? Would it also lead to improvements when there are periods of plentifulness of water?
Goldbond discovered that lower prices might in fact not be the case under these circumstances, due to the extreme complexity of the New Zealand electricity market.
This is kind of perplexing, right? But this is precisely the reason why we spend the time investigating game theory models and equilibrium models.
While Goldbond's findings have thrown up many issues, the mathematicians agree that it is not the final word on what will happen in reality.
Whether or not these examples are going to eventuate in the New Zealand electricity market, I can't tell. What I can tell you is that it's possible for them to eventuate, right? So I'm, in a way, providing a warning.
The scope of mathematics is truly enormous. It describes our world and props up our applied sciences. And in its pure form, it is quite simply the joy of solving a puzzle that drives it forward.
Mathematics is a language in its own right, one with its own poetry and beauty. But it's more than that. It's the best way to describe the world around us, which might lead us to believe that whoever created the universe used a lot of maths to do it.